Our next and final step for today is to take control over all allocation that happens during interpret. For example, when we make a new continuation record with +k, that is an allocation that we're going to handle ourselves now by implementing malloc. And to go with that, since we are taking control over the representation of records, we can't use pattern matching built into Shplait anymore to find the right case and pull out the pieces. Instead, we'll have to use more primitive operation that looks like the kinds of things you can write in assembly code. And the reason we have to do this is at the machine level, all we get are a handful of registers and a big array of memory. Registers usually have names like RAX, RBX, and maybe stack pointer, but we can just use the names that we want to in our interpreter, and it's still the same thing. But what goes in those registers and what goes in memory is all just numbers. Every slot in memory has a number, each register has a number. Some of those numbers correspond to things that are used in a Mo program, like this Mo program maybe is adding 1 and 5 and 2 in some way. But a lot of the numbers are being used just as the name of different parts of memory. That is, registers have names, but different parts of memory do not have any names at all. We refer to parts of memory using just numbers again. And those numbers are the same sorts of numbers as ones we use for Mo numbers when we look at things at this level. So how do you know when you see a number what kind of number it is? Well, it depends on what it's representing. In our old implementation of the interpreter, if we use the int type, then we can just use an int at a corresponding place in memory. But if we had an object like an x per d or an emp or a value or a cond, any of those types, basically any type except int, then we need to represent a value of that type using an address. That is a number that's going to refer to someplace in memory. Note that our registers in our interpreter are always going to have addresses. That's because expr has an expr in it, capital E expr, which needs to be represented as an address, and so on. Even if the expr is an int d5, say, it still needs to be an int d record with a 5 inside of it, and that's actually what we're seeing right here. So what are these other numbers, like 8 and 9? Well, that answers the question of, when you look at address 10, how do you know what kind of expression this is? These numbers that are at the beginning of every allocated spot are tags, and the number there represents which kind of variant we are. So it turns out that 8 is going to be just a int d record, and 9 is an add d record, whereas 15 will correspond to a int v value. So that's how we're representing everything just using numbers. And so what we see in this translation of the code is expr is now going to have just a number in it that represents an address, and we will use the ref operation, which takes these two numbers, just adds them together and looks at that place in memory. In other words, we look at offset 0 from the address in expr and see what number we have. The number that's at the start of that address should be a tag that tells us what kind of expression we have. So 10 is going to be our number that means plus d. And then where we used to call +k with r, mvreg, and kreg, we can still refer to mvreg and kreg directly, but r came from the pattern match pulling out the second part of the register from expreg, of the address that's in expreg. And now we need to explicitly take that address, use offset 2, which is where r is, to get that next argument to malloc 3. And there's a 3 in the malloc 3 just to say we have 3 things in addition to the tag. Meanwhile, this tag 1 is going to correspond to +k. So overall, we need to take all of our variants across all of our types and give each of them a unique tag. So done_k is going to be represented with 0, +k with 1, int d with 8, plus d with 9, and so on. Int d and plus d are things we don't need to allocate as we interpret because they correspond to the code, but our interpreter will need to look at code in memory, and so it needs to have different numbers for those different code variants. Meanwhile, we do allocate +k's and int v's and close v's as we go. So just as another example, the molt_k case in continue will correspond to taking the k register, that's an address, looking at offset 0 to find what tag we get. If it's tag 3, then where we used to do things with r, emp, and k, which were the 3 parts of that record pulled out by pattern matching, now we explicitly dereference the address in kreg at offsets 1, 2, and 3 to get the same sort of references out. We will implement malloc ourselves. To do that, we need a representation of memory, and we'll just use a big array of numbers. So we will use size 1500 slots in our memory, each initialized to 0 originally. And then we need an allocation pointer that we'll set to be 0, and that is at the start of memory. Each time we need to malloc something that has 3 fields, we'll use malloc3 and also provide the tag. And then we fill in 4 slots in memory using the tag followed by the 3 payload parts of the allocated object. And then we bump the allocation pointer by 4 because to allocate a record of size 3, we need 3 plus the tag, that's 4 slots. And then finally we return the old value of pointer reg. This is a standard assembly trick of just subtracting back off something that you incremented so we don't have to worry about a place to store the old pointer reg. We return that number. That number is an address where we just allocated this object. So again, we're going to take every use of a variant constructor, like int d or int v, turn it into a call of malloc, malloc1, malloc2, malloc3 as suitable. And those malloc arguments are always going to be numbers, and the result is going to be numbers because everything is a number.